This is video 10 of Unit 9, the last video of the unit. We finally made it. And here we will talk about orbital notation. Now, orbital notation is a version of electron configuration that represents orbitals. Before, when we had 2p4, this configuration shows you the shell, shows you the subshell and the electrons, but it does not show you the orbitals. So orbital notation will actually give you the orbitals. And for this, we're going to draw either lines or boxes to represent the subshell and the orbitals. So, we're going to draw boxes above the subshell, and the boxes or lines will be representing orbitals. So, for example, here, an S subshell has one line. That's because an S subshell has one orbital. A P subshell has three lines because a P subshell contains three orbitals, and that's the idea. Now, sometimes, as you'll see, they'll actually draw these according to their energy levels, so you can actually put the S a little higher, along with P, just to show that the second shell is further from the nucleus, higher in energy compared to the first shell. But that's the idea. Now, electrons either have a positive or a negative spin. This will be important. One property of electrons that we haven't talked about is the idea of spin. And so one electron will have a positive spin. Oftentimes we'll use an up arrow to represent that. The other one, a negative spin, a down arrow. And this S and N refers to the fact that electrons can actually create a small magnetic field, like a north and south magnetic field. So that's what we're going to use for electrons. We're actually going to use arrows to represent electrons in this configuration. We'll first add the up electron, and then to each orbital. It says go ahead and add it to each orbital, and then we'll add the down electron to each orbital until the subshell is filled. Now, so what this looks like, notice that we fill each subshell at a time. So we fill the first S subshell with up down, the second S subshell with up down, and then the third subshell, which is the 2p subshell, we'll actually put all up electrons in first. So it'll be incorrect to do it like this. 1, 2, 3 would be incorrect. You actually have to fill all the up electrons first. Now, this is called Hund's rule, and it's an important rule that was discovered, and this is true for elements. We can actually experimentally verify that all the up electrons are placed in first, and then the down electrons are filled. Now, what an orbital is, recall, is an orbital is a three-dimensional position or a three-dimensional area around the nucleus where the electron can be found. So that's what we are talking about here for orbitals. So, for example, for the S orbital, which is spherical, this is the S orbital, you can say that the S orbital holds 2 electrons. Now, you can see in the back, you got a p orbital going this way. That will hold 2 electrons. You have another p orbital going this way. That will hold 2 electrons. And then you have a third p orbital holding 2 electrons. And these orbitals are represented here then by boxes. And so sometimes you can be a little more specific. You can call this the 2px, 2py, 2pz orbital. In our case, just the 2 and the p will be sufficient. This, by the way, is for the element carbon. Alright, let's go ahead and try a few. Write the orbital configuration for oxygen. Now, if you take a look at oxygen, and then we'll do chromium. We don't have a periodic table available for this one, so let's go ahead and consult oxygen on the periodic table. Here is the periodic table. You'll find that oxygen sits as element 4. Looks kind of like this. So we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. So oxygen sits right here. So what we'll have to do is we'll actually have to go through and write the configuration of 1s2, 2s2, and then 2p4. Let's go ahead and do that, except what we'll do is we'll kind of spread them out a little bit. So this is for the element oxygen. So I'll write 1s2, 2s2, and then 2p4. So it's exactly what we've done before, except what I've done is I went ahead and spread them out a little bit. Now, technically, you usually don't list the 2. You don't list the number of electrons. You simply draw the orbitals. Now every s subshell has one orbital, so we'll draw one line above the s's. The p subshell has 3 orbitals, like so. Now we recall that this has 4 electrons, this has 2 electrons, and this has 2 electrons. So I'm just going to put those greens in just for us to see it a little better. And then we can go ahead and put the electrons in. Now it's important to work one subshell at a time. So we're going to put 2 electrons in here. One will get an up arrow, the other a down arrow. Now you'll see me draw half arrows just for the sake of saving time, but feel free to draw full arrows if you'd like. You can do it like this. Now we work on the second S subshell. We'll do an up and a down. And here's where it's really important. The third subshell, we'll have to do all ups first. 1, 2, 3, we have a total of 4, and only then can we put a 4th electron in. And in the end, this is what it should look like. We can get rid of these electrons here, and this would be the orbital diagram for the element oxygen. Let's do another one. In this case, let's do chromium. And looks like chromium, if we keep going, is in the D subshell. Chromium sits right here, and we have to go through a few elements here before we get to chromium. And chromium is element number 24. So it's actually a little further down this way. It's the 4th element in the D subshell. So a little trouble there, but it should be the 4th element. 1, 2, 3, 4. So it's this element right here. So now we have to go through the rest of the P subshell. And then actually we have to do 2 more. There's another S, another P, and then finally a final S. And then we'll stop at number 4. Let's go ahead and write out chromium's configuration just the regular old way. Here's chromium. Let's do 1s2, and then leave a little space between them. 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, in this case would be 4, 3d4. So this is the regular configuration of chromium. Now, what we'll do is, again, we'll draw lines. Now, the thing is, you can either draw the lines above or below. It's actually fine to draw them below. In this case, let me go ahead and draw the lines below, because you can do it either way. There's really no set way of doing it. Every S subshell has 1 line, so I'll go ahead and draw 1 line below every S subshell. That represents 1 orbital in the S subshell. Every P subshell has 3 lines, so I'll draw 3 lines here. I'll draw 3 lines here, and then I'll draw 5 lines. Okay, there it is. The D subshell has 5 lines. It's important to draw all 5 lines for the D subshell, so it'll look like this. And you want to spread them out to where you can see clearly the divisions between the subshells. You don't want them to blend in, because technically these are different subshells. Alright, and then I can put the electrons in. Now for the electrons, I'll work 1 subshell at a time. In this case, I got 2 electrons in the first subshell, so 1, 2, 2 in the second, 1, 2, 6 in the third. Now make sure you put them all, according to Hund's rule, as ups first, 1, 2, 3, and then downs, 4, 5, 6. The next subshell has 2 electrons. Here I have 6. Make sure you put all the ups in first, 3, 4, 5, 6, and then the downs. And then the 4s2 has 1 up, 1 down. And then we've come to the last one, the 3d4 subshell. So we have 4 electrons, 1, 2, 3, 4. What we end up with here is an empty orbital. This will be an empty orbital, an unfilled orbital. And usually we don't write in the electrons, so we can get rid of those electrons. And that completes for us chromium's orbital notation. Now, you could have done, if you're asked, you could have done the condensed version, the noble gas version of it, and usually for chromium, that's what you'll do. So for chromium, really, we have the noble gas that comes before chromium is argon, so we'll actually put argon in brackets, and argon represents the first 18 electrons. So all the way up to here would be argon. And then all we have to do is 4s and 3d. So you can put the 4s subshell and the 3d subshell. Again, the S has 1 orbital, the D has 5. You can go and put 2 in here and 4 in here. So it is possible to do the noble gas version of this notation, which will be the way to do it for many of these elements. Alright, go ahead and take a moment and try both of these on your own. Write the orbital notation for phosphorus and copper. Now, we're going to say just a few more details about this, and I mentioned this before, but orbitals can actually be written according to their energy levels. And this allows them to be spaced out. So here, for example, you can see that the 1s orbital being closest to the nucleus is lower, but the 5s orbital is highest, being higher in energy. And what you've got is the nucleus is down here, and then as these are essentially energy levels coming away from the nucleus. That's what this is. So sometimes to save space, we just draw them in a single line, but we realize that these are actually ordered according to energy. And oftentimes, this detail is omitted. Now here it says, note that the 5s orbital is, or rather the 4s and the 5s orbitals are actually a little strange. What we mean here is, as you're filling this, you're actually going to go 4s, and then if you take a look, the next one is not 4p, but 3d. You'll notice that the 3d goes after the 4s, and then you go to the 4p, and then after you've done the 4p, you do not go through the 4d, you go to the 5s. So notice the 5s is actually lower in energy. I mean, you think that the 5 is higher than the 4, but not always. The s's are actually lower than the next d's, or the previous d's rather. And the reason I say this is the periodic table actually lists them. This is essentially the idea of the d being n minus 1 that we talked about, or the f being n minus 2. You can see that the f here is even higher than the 5s. Rather, the 4f is higher than the 5s. All this says is that it's according to the periodic table, and the periodic table here is the document that you can use to make sure you do this correctly. Okay, we have one more important principle, and this comes from Mr. Wolfgang Pauli. You have a fine picture of him here, and it's called the Pauli exclusion principle, and it says that no two electrons can have the same 4 quantum designations. What this means is that every electron in an atom has to have a unique address. In other words, its shell must be different, its subshell, its orbital, and its spin must be different. And an orbital diagram actually shows this visually. So an electron, for example, one electron can have the address 2p4, and it could be in the third orbital spinning up. So that's what this means. Essentially, this shows the address. This shows the complete address of that electron. And every single electron, its partner that's downspinned, has a slightly different address. Its different address is the fact that it's spinning down, not up. So you cannot put all electrons. So you will not be able to do this, for example. This would be wrong, because this violates the Pauli exclusion principle. And you can't have two electrons, two of the same electrons being in the exact same position. Every electron has its own address, has its own position in the atom. Now, a few more ideas and we'll finish. We're going to define something called inner shell electrons. And inner shell is just like it sounds. They're inside the shells, or in the lower shells rather, also called core electrons. So these are the electrons that are not in the highest occupied energy level. If you take a look at this configuration, what we've got is we've got 3 as the highest shell. Remember, this big number represents shell. And in the third shell, we actually have 2 plus 2, we have 4 electrons in the third shell. But these electrons are in the highest shell, which means everything lower is called the inner shell. So these are your core electrons. This element has, if you total up 2, 4, 10 core electrons. And these core electrons are actually neons electrons because of the noble gas configuration. But this is what we mean by inner shell electrons. So a quick little example. How many inner shell electrons in this configuration? So again, we'll do the same thing. We'll find the highest shell. The highest shell here is 4. So everything else are called core electrons, or inner shell electrons. And we got 2, 4, 10, 12, 18. We got 18 core electrons here. And that corresponds to argon. Alright, how about cobalt? If you take a look at cobalt, if we write out cobalt's configuration, I think we've done it earlier, that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d7. This is cobalt's full electron configuration. Now if you take a look, ask yourself, what is the highest shell here? The highest shell is shell 4. shell 3 is actually lower, which means this is going to be the outside, and then everything else are going to be core. So including this 3D. This is a core, and so are these. So this example is a little strange. This is going to be the outer shell, and then these greens are going to be the inner shell. So we can actually calculate how many we have here. We got 2, 4, 10, 12, 18, and then 7 more. So we actually have 25 inner shell electrons in the element cobalt. This is true of d block elements. You'll actually count their 4 electrons and not their 3 electrons. Try this yourself, make sure you understand this. And then we're going to finish up with something called valence electrons. Now, valence electrons is a fancy word for outer shell electrons. Valence has been created to show that these are the outer shell electrons. In other words, they're on the outside. They are in the highest occupied energy level. So in this case, 3 is the highest occupied energy level, so any electron in the third shell is called a valence electron. So in this case, we have 1 valence electrons. We have 10 core electrons. Alright, so let's do the same thing. How many valence electrons in these configurations? So first of all, we find the highest shell. In this case, here's the highest shell. So this highest shell has only 1 electron. So simple as that. Alright, the second one, the highest shell, is shell 4 again. And we have 2 here, plus another 3 here. We have a total of 5 valence electrons. Also pretty simple. If you take a look at beryllium, now why don't we consult the periodic table for this? We have, I think, beryllium and gallium. Let me show you. You can actually visually see these. So here's beryllium. If you take a look at beryllium, its valence shell is the highest energy level, which is 2. Beryllium actually sits in the second shell, which means anything below that are actually inner shell electrons. So these are inner electrons. And then anything that's in boron's shell are outer electrons. So actually you can visually see that, not boron, sorry, beryllium has 2 outer shell electrons. If you do the same thing for gallium, here's gallium. What gallium has is this represents 4p, this represents 4s, remember this represents 3d. So for gallium, 4 is the highest shell, and actually in the 4th shell, you've got 1 electron here and 2 electrons here. And so gallium actually has 3 outer electrons, or 3 valence electrons. So simple as that. Hopefully you can use the periodic table to do the same thing. And go ahead and try some of your own. Pause the video, try these. And the last statement we'll make is that the valence electrons, which we've just finished talking about, are extremely important. We will be focusing on them a lot. They are the electrons that are involved in chemical bonding. So the inner electrons, inner shell electrons, the core electrons, just kind of sit there right in the middle or closer to the nucleus, and they actually are not involved in chemical bonding. But these outer shell electrons that are on the outside, they will be involved in chemical bonding. So anytime an atom, for example here if you take a look at the atom carbon, carbon has 2 core electrons, and those are not involved in the bonding. They're on this inner shell that's not connected to any other elements. But its outer shell electrons, this one here, is actually the one through which it connects to your other element. This is a compound called CH4. This is called methane. And you'll see, we'll study this in much more detail, how carbon brings 4 of its valence electrons to share with bonding with the hydrogens. And that's why there are 4 connections that it makes. Alright, so this finishes up the chapter for us.